Okay, so in this lecture, we will derive formally the different order of moment equations for the velocity. Okay, and we will see that finally how it can be related to something which we already know. Okay, maybe after this lecture that will not be 100% clear, but gradually it will be clearer. Okay. So first you see that we start by deriving the zeroth order moment equation. Okay, that's the quite automatic thing, and zeroth order means velocity to the power 0. Okay, and this is nothing but 1, or I mean simply this is the what is the conserved quantity for that, because we know like only if we just try to derive a moment equation for something which is conserved in a binary elastic collision, then only for collisional Boltzmann equation we will get rid of the collision integral. Okay, after integration. So what is that? This is nothing but the number conservation. Okay, two particles remain two particles, right? So that is the thing. So in order to derive the corresponding moment equation, we have to multiply the whole equation by either 1 or any arbitrary constant, and then we have to integrate it in U space. Okay, this U space. Okay, so and that's exactly what we have done here. And the right hand side, as we know that now here is the catch, that now if it is a collisionless, now from this we cannot easily understand whether this is a collisionless Boltzmann equation or collisional Boltzmann equation, because this is true for both collisional and true for both collisionless and collisional Boltzmann equation. Okay, and that is something you have to realize. Okay, now here what we do, that we just integrate everything in U space, and we just say that irrespective of this is collision or collisional or collisionless Boltzmann equation, the right hand side will be 0. Okay, this. Now the first term, okay, we try to evaluate term by term. So now the first term is integration del f del t d cube u, and here this is really important throughout the course to understand how these reductions are happening. Okay, so del t is an explicit, this is an explicit, the partial time derivative, so it is activated when the system, the function has an explicit time dependence. And this integration is over in U space, so del t and u, del t and the integration, they are totally under two different variables. So u and t, there you know, like f is a function of r, u and t, so all of them are independent of each other. Okay, although you know, like both r and u, they're implicitly, they're implicitly depending on t, but that means when I'm saying that f is depending on r and f is depending on u, there is an implicit dependence on time, but explicit dependence of time is independent of its explicit dependence of r and u. Okay, and that's why this del t and this integration can commute. Okay, and del t can come outside. Okay, this one, and you can simply have del t of integration f d cube u, and what is f d cube u integration? That is nothing but the number density, so that is nothing but del t of n. Okay, now what about the second term, that was integration u dot nabla f d cube u. Nabla is a space operator. Now f has space dependence as well as time dependence, may have as well as velocity dependence. But u and nabla, once again, nabla is a pure space operator, so it's a function of r in that sense, and u is the kinetic velocity which is independent of space. Okay, so u and nabla, u is independent of this space operator. That's why I can write this one as divergence of fu. So u will act as a constant vector in front of this nabla, so it will simply be divergence of fu d cube u integration. Now here is a common source of mistake. Now some students can tend towards an integration using Gauss's divergence theorem. Well, I have a divergence, I have a volume integration, but this is not true because the volume integration is on velocity space and the divergence is for the pure space. So this is not going to work. Now what will be the proper reduction in this case? This divergence is a space operator, whereas this integration is on the velocity space. So this divergence will come out. And what is inside? Inside you have uf d cube u. And what is that? Once again, this thing by n is equal to angular bracketed u, which we call v. That is the average velocity, or I said that it's a bulk velocity or fluid velocity, v. Then I can easily say this thing is equal to n times v. So this is nothing but this is equal to divergence of nv. Okay. Again, the last term, integration over a dot velocity space gradient times, gradient acting over f times d cube u. Now you see, here I have an assumption a priori a can or cannot be a function of velocity, but most of the cases it usually depends on space coordinates. For example, if it is a gravitational force, then most of the cases the conservative force fields, they depend on force. But in nature we have several force fields, okay, which are very, very relevant, but they are actually depending on velocity, and that's why whether they are conservative or not, that's a bit subtle. For example, magnetic field, which is a velocity dependent force. Okay, and for that also you can show that although this is not independent of velocity, it's a dependent of velocity, but the divergence is 0. Okay, so whether a is independent of velocity or whether a is a divergence-less vector, divergence-less means in terms of the velocity divergence. Okay, in both cases you can write this. So this is an expression which actually is true for both electrostatic, magnetic, and also the very popular gravitational force. Okay, this one. So this reduction you can do. Now here we are just thinking of, because we don't have charged particles here, just the gravity, okay, in mind. So a just can enter as a constant vector, okay, because a is a function. A can be a function of time, a can be a function of space, but not a velocity function. So it will come inside. So now you have a divergence, velocity divergence of some quantity integrated in, volume integrated in velocity space. Now I have the right to use Gauss's divergence theorem. And that's why you have this thing, and you can then say that, okay, for this volume I can extend the containing surface to infinity, and so that at infinity I don't have any matter or anything. Okay, so on that like surface, this flux is 0, this flux is 0, and that's why I have a vanishing quantity. Okay, so finally this term is not contributing at all, this forcing term, and the zeroth order moment equation simply becomes del n del t plus divergence of nv is equal to 0. Now this is the most general form of continuity equation. Now of course, in very popular cases, we actually, what we call for fluid dynamics or everything, okay, what we call the continuity equation looks like this: del rho del t, which is written in red, okay, this one, okay, and plus divergence of rho v is equal to 0, and that is exactly can be immediately obtained if you just multiply this equation by the mass of one particle. Okay. Now, what about the first order moment equation? So you see that already something, so the zeroth order moment equation gives us something which we already know in a different perspective, that is the framework of fluids, right? Now here we have not, to be very honest, we have not considered till now any continuum or anything. We have just did some integration in velocity space for the kinetic systems, and we simply said that we are deriving moment equations. Okay, there is no don't confuse that at this step we are not even talking about the fluids. Okay, but we have this continuity equation. So first order moment equation, this is the second, this is the next automatic step. Okay, so then what we have to do, we have to multiply the whole thing by u to the power 1, factorial u to the power 1, and which is u itself, multiplied to this equation, and the right hand side again, irrespective of whether it is collisional or collisionless, it will be 0. Okay, because u is something which is component wise and actually vectorially conserved in a binary elastic collision. Okay, now this u del f del t, the first term is integration u del f del t del cube u integrated over u space. Then what is happening, again del del t and u, they cannot see each other, so u can enter inside del del t, so you have something like this. Again del del t and this integration, they are independent, so del del t can come out of the integration. And what is inside? Inside this is nothing but, you all know, that is n times v, that we have already seen. So this is ddt del del t of nv. What about the second term? The second term is integration u times u dot nabla f d cube u. Again, here you see that you have now this u and nabla, they are independent of each other. So again u comes inside the nabla operator. Nabla is a space operator. So you have u nabla divergence of fu d cube u. Now in the assignment 0, I asked you to do something, a tensorial identity, which is very, very important. That is, if you have something like this, divergence of two vector, tensorial product of two vectors, then it should look like this: b plus a dot nabla b. Although a priori at the first look it may look like some symmetric thing over a and b, they are not. So you see, in the first case you have a divergence of a which is multiplied over b. In the second case, it is the gradient is now operating over b, but is a different way. Okay, in both cases. Okay, so you see that this is, so if you just interchange b and a, this is not exactly the same. Interchanging b and a, this is not exactly the same, because a tensorial b has a symmetric part and also has an antisymmetric part. Just read about that. Okay, that's a very interesting thing to cultivate. Okay, now using this identity, you can write this thing as this tensorial divergence of this tensorial product of two vectors f u tensorial u, okay, integrated in u space, minus f u dot nabla times u integrated in u space. Now this one is 0 because nabla is acting on u and nabla is a space operator, so nothing to do. So this is 0, and you have simply the divergence of this tensorial product. Okay. Now at this point we can do something much more interesting. We express the u at every point as the mean value of it and the fluctuation with respect to the mean. Okay, so the mean value is nothing but the angular bracketed u or v plus we call the fluctuation as C. Okay. So the C fluctuation means that the statistical average of C will be 0. Okay. The statistical average of fluctuation is always 0, because if you do the average in both sides, U average will be equal to U average, so which is again U average plus C average, and this will be cancelling each other, giving C average is equal to 0. Okay, that is easy to see. Now if we write in this way, okay, finally this term where we ended over here, this one will now be written in terms of this divergence of if U tensorial U integrated in U space is equal to, then every U can be written in terms of V and C, and then you will have actually, by doing tensorial product, 4 terms. So the first term will be including V and V. Okay, the 2 terms will be a mixture of C and V, where you can exactly show that both the terms will vanish because of the simple method, a simple consideration that the statistical average of the fluctuations, they are vanishing, and the final term will be containing only C, and this is the tensorial product of the fluctuations. Okay, and this is actually is nothing but it's another way of writing n times C tensorial C, right? That thing, okay, so everything is under divergence, so that thing is known as another tensor P, which is a second rank tensor by the mass of the particle, and this P is known as the pressure tensor. Now the question is that how we know that is the pressure tensor? Well, we actually don't know. This is somehow from when we mix our previous knowledge of kinetic theory a bit, and we also mix our previous knowledge of fluid mechanics, then only we see that this, if we identify this tensor as P or the pressure, then everything looks actually matching. That's why it is the pressure tensor. Okay. Now it is try to understand these equations. What I am doing here, I am trying to derive the moment equations starting from kinetic equations. Now finally you will see that the target is to derive the fluid equations starting from the kinetic equations, right? But well before that, the engineers, they already derived fluid equations, sometimes by empirical things, sometimes by macroscopic considerations. We also do something using macroscopic considerations. Okay, in normal fluid dynamics book, you will always see the derivation of the force equations or the continuity equations. The derivation is using the macroscopic considerations. Okay. So finally, to be very, very honest, this is just, this is not something new what we are doing. This is, we know something, the results, the final relations we know. Now we try to reachieve or recover those things starting from the microscopic theory or the kinetic theory. Okay. Now you see here, this part is the part where the term is including, containing only V. Okay. So this is the divergence of in V tensorial V plus divergence of P tensorial by M. Okay. Finally, we have the last term of the forcing. So U times A dot nabla U acting on F integrated in U space. Once again, you see A is a function of space operators usually. So A should go inside this, and that should give you divergence, velocity divergence of FA. This is also true if A has a velocity dependence, but A is divergence less. That means divergence of U dot A is equal to 0. That is also possible, and that is exactly the case for magnetic field. Okay. So if you have this, then you can again say that using that tensorial identity, this is nothing but integration velocity divergence of the tensorial product of FA tensorial U d cube U minus integration FA dot velocity gradient u d cube u. Now this is 0 because now you can use here the Gauss's divergence theorem. Remember, here we could not use Gauss's divergence theorem because this is spatial divergence, this is velocity integration. Here you can, and you can make it 0. Okay. What is about this? This is easy. You can just expand and check. This is nothing but is equal to, this is minus integration f a d cube u. And what is that? Anything, any quantity, when this is just integrated with f d cube u, that is nothing but n times the angular bracketed of that quantity. Okay, so it will be minus n times angular bracketed a. A is nothing but the acceleration. Once again. Okay, so the total first order moment equation can now be written as del t of nv plus divergence of nv tensorial v is equal to minus divergence of p tensorial by m plus n times a vectorial. Okay. Another alternative way of writing this is if you expand everything like here, just use the tensorial notation, tensorial identity once again, and use the continuity equation. Then finally you will see there are two terms that will be cancelling due to continuity equation, and you finally will have n times. You finally will have something like this: n times this. And this, the right hand side should look like this. Now if you multiply everything by m, then it will be a row everywhere. So here it will also be so basically, once again, so this is okay, so there will be row, and that will simply be divergence of p then, and that will be rho. Then you again divide everything by rho. So finally you will have this form. There is nothing. Here you will have this quantity divided by rho, and here there were a rho, so rho will be divided by rho, and finally giving you acceleration. The best way is to do it by yourself. If you do it by yourself and you cannot reach there, please let me know. Okay. Finally, now one thing is that you see this is nothing but the momentum equation. Okay. So of course here it should look like some acceleration equation, but it is actually momentum equation in the sense that this is an evolution equation for the evolution of momentum, so which is roughly called the momentum equation. Okay, so here for example, if you just multiply this by m, so that will be then nothing but m and v, del t of m and v, and you multiply actually throughout. So I'm just talking about this first term, and multiply of del t of rho v is nothing but rho v. What is that? This is nothing but the momentum density. So this is the evolution of the momentum density. That's why it is called a momentum equation. If you try to understand, this is nothing but a Newton's law. This is a law, equation of force. So acceleration, right, is equal to some forcing. So this is the acceleration, the total thing. So this is actually, you will see that in Newton's law, these two things get combined to give dv dt, and that is equal to, this is the whole source of force. So this is the acceleration equal to force. Acceleration equal to force by mass, of course. Here when we are talking about, now you will see when you are talking about macroscopic things or the continuum, we will not talking about per unit mass but per unit volume. So then there will be, we will talk about the densities. Okay, so here this is the thing, this is acceleration, this is this is the force density, which is equivalent to acceleration. Okay. Now let's talk about second order moment equations. Okay. Now as we discussed earlier that in order to obtain the second order moment equation, we need to multiply the Boltzmann equation by u vector to the to square, raised to square, and that is nothing but the tensorial product of u and u. But u tensorial u is not known to be conserved in a binary elastic collision. That we don't know. One thing we know that u square is conserved, and one can actually show that. Please do that at home. That is a very good homework. Please do that. That if all the components of u, they are conserved because of the momentum conservation in a binary elastic collision, and u square is also conserved due to the kinetic energy conservation, then u minus v whole square is also conserved. V is a constant once again. Okay, so v is something which is which is a function of x and t, that's true. But here in this case where you are talking about like for example, I mean how to say, I mean in kinetic case, in kinetic level, when we are talking about kinetic level, so v just is a constant, because I mean v has a unique value for the total system. So this is an averaged quantity, it's a mean value. Okay, so just remember that when we are talking about collisions, we don't talk about the change in position. We are talking about a simply a point position which does not change in a collision. So if v is a point, I mean property of position only, then in a collision that should not change. Okay, so just using all these facts, try to show that u minus v whole square is a conserved quantity. If it's a conserved quantity, then we can derive a moment equation. So this is I mean a hybrid moment equation. Okay, if we multiply the collisional or collisionless Boltzmann equations by this and then integrate in u space. So once again, as I just said, that second order moment equation is not a pure second order moment equation, but it's the trace of second order moment of the fluctuation velocity c, which is equal to u minus v. So this is nothing but c square, right? Now, in fact, to obtain realistic equations, that is something very important. We multiply by half m into u minus v whole square, because something, if we recover something which we already know, we feel happy, right? So if one does correctly the calculation basically, and this calculation is a bit longer, okay, so I will give you the solution after some weeks, but first try it at home. Okay, so this is a very good exercise. If you do the algebra correctly using vector identities and the corresponding definitions correctly, then you will see the equation, the moment equation should look like this. Del t of rho times epsilon plus divergence of rho epsilon v is equal to minus divergence of q vector minus the pressure tensor doubly contracted. This is a double contraction sign. Okay, doubly contracted in with lambda tensor. Now what this epsilon, q and lambda, they are new here. So where q is nothing but half rho angular bracket u minus v times u minus v whole square, and this is known as the heat flux vector. This is a special case or the trace of this third order tensor, which is known as heat flux tensor, which is nothing but the, so heat flux tensor should look like this one. Okay, it should look like this: u minus v tensorial u minus v, u minus v tensorial u minus v. Okay, so it should be represented by a cubic matrix. Okay, like this. So in 3 dimension it will have 27 components. Okay, but we were not going into this because we are in a simplistic case where we are multiplying with this term, the whole thing, so we have, that's why the a vector out of this third rank tensor. Okay. So, and what is epsilon? Epsilon is nothing but half of angular bracketed u minus v whole square. So you see, this is nothing but something like a fluctuating energy, fluctuating kinetic energy type of thing. So if you constitute a kinetic energy type of thing, starting from the fluctuation vector velocities. Okay. So once again, this is equal to this. And what is this capital lambda tensor? That is the half of the gradient of velocity plus the gradient of velocity transpose. So this is a symmetric matrix by definition. Okay. So using all these things actually, and this is, doing again the same trick what I just suggested for the first order equation. Equation 8 can be written as rho times del E del T plus V dot nabla times E is equal to minus divergence of Q minus P doubly contracted with lambda. Here what I just did, I expanded and used the continuity or the zeroth order equation. This equation is known as the energy equation. Now, just by putting an analogy to the momentum equation, you can understand why it is called energy equation. Just one thing is that the continuity equation, the momentum equation and the energy equation, okay, so if we just look back, they make total 1 plus 3 plus 1 total 5 equations. Continuity equation is one scalar equation, energy equation is one scalar equation, the momentum equation is one vectorial equation, so 3 component equations. But what is the number of variables? The number of variables, this is much larger. You have rho, you have Vx, Vy, Vz, epsilon, 6 components of P. Why 6 components? Because this is a symmetric matrix. So in a symmetric matrix, you will have 3 diagonal components which can be different and 3 off diagonal components which can be different. Okay, so that is the then 6 unknown different components of pressure tensor. Then Qx, Qy, Qz, the 3 components of the heat flux vector. So total 6, 3, 9, 10, 14. 5 equations, 14 unknowns. So no way of, and there is no apparent relation between them for an arbitrary distribution function f. If we don't know what f is, then we don't know a priori how, if there any relation between epsilon, rho, p, q, v, etc. So a priori, 5 equations and 14 variables can never make a dynamical theory. Okay. So as we understand, we can make a dynamical theory only when we can reduce the number of unknowns. And that is possible only using the knowledge of f, as we will see. Sorry. That is possible using the knowledge of f. Okay. Now one should note that the 3 moment equations which are derived above can be derived both from collisional and collisionless Boltzmann equations. This is, I am repeating, but this is very interesting and important to understand this point. Now secondly, the zeroth order equation contains first order moment, the first order equation contains second order moments, and so on. That is very, very interesting. In the zeroth order equation, if you see attentively, in the zeroth order equation you have V, which is the first order moment. In the first order equation, you have P, which is the second order moment. Okay, of course I understand for fluctuating velocities, but this is second order, somehow second order, or at least you can also say from here, but that is okay. In any case, you have some higher order tensorial things. Yeah, for second order you actually have a third order. So here you cannot see that, but actually you can again say that this is the trace of the third order thing. Okay, and this is also the trace of the second order thing, that's why. So in any case, nth order moment equation should contain the n plus 1th order moment. Okay, and that is exactly the problem of hierarchy. That is, you can never close the systems. Okay, so in collisional case, the system can be closed easily. We already know the equilibrium distribution, so we can, as I just said, that by the knowledge of that if we can reduce, and actually we will see that this is the case when we will derive the ideal fluid equations, that by using the knowledge of this equilibrium distribution being the Maxwell-Boltzmann distribution, we actually could relate some of the unknown variables to make a finally dynamical theory. But for a collisionless system, we have no hope. We can continue to derive moment equations unlimitedly without closing the system. Okay. Still, after all these things, there is a good news. And what is that good news? Even for the collisionless systems, the collisionless moment equations are of very, very interest in astrophysics. And we are talking in the framework of astrophysics, so that's why we will discuss all these things. And that is the, theme of what we call Wood limit that we will do in the next lecture. Okay, thank you.